Classical economics relies on a specific mathematical assumption that human society can be modeled using the same optimization calculus we use to determine the maximum height of a projectile. But when you apply that math to social exchange, the variables clash. The outcome for one person depends on the unknown choices of another. For decades, economists treated markets like simple multivariable optimization problems. They assumed you could find perfect equilibrium by plotting variables, like supply, demand, and prices, and solving for a single maximum peak. In 1944, mathematician John von Neumann and economist Oscar Morgenstern published Theory of Games and Economic Behavior. Their objective was not to make minor adjustments to the existing equations. They argued that the underlying mathematical tools of classical economics were structurally incapable of handling the realities of human interaction. To understand how they rebuilt this system, we have to look at exactly why optimization calculus fails in a society of multiple agents, and how injecting probability into subjective choices creates a rigorous numerical scale for human desire. Until this mathematical bedrock was replaced, economics lacked a rigorous way to calculate the outcomes of interacting wills. The flaw in classical economics starts with what von Neumann and Morgenstern called the Robinson Crusoe model. Imagine an isolated individual on an island. This single person controls all the resources and allocates them to satisfy their own wants. This chart shows the Crusoe economy. Crusoe dictates every choice, a standard multivariable calculus problem. The outcome ascends to a mathematically pure peak. But a social economy introduces a second participant. Neither controls all variables, creating a mathematical contradiction. The unified peak breaks apart. A participant in a market cannot treat the actions of others as dead, passive statistics. Every variable controlled by someone else is guided by their own rational and often opposing interests. Social exchange is simply not a conditional maximum problem. Because the classical mathematical toolkit is useless here, they had to invent a new framework, the theory of games of strategy. To build the mathematics of strategic games, however, the system requires precise inputs. A mathematical model cannot run on vague assumptions about human preference. It requires strict quantitative values. At the time, economists generally rejected the idea that utility could be quantified. They argued it was an internal psychological sensation, and therefore unmeasurable. Von Neumann dismissed this objection by pointing to the history of physics, noting that the exact same argument was once made about heat. This diagram shows an abstract ordinal ranking next to an early thermometer. Early scientists only had an ordinal concept of temperature, knowing one body felt warmer without exact numerical distance. Later, thermodynamics quantified heat into a rigorous, additive numerical scale, like Kelvin. Just as physics had to invent absolute temperature to progress, economics needed a mechanism to mathematically quantify subjective utility up to a linear transformation. To extract hard numbers from subjective feelings, von Neumann and Morgenstern started with two requirements. First, completeness. The person can always choose which of two outcomes they prefer. Second, transitivity. If they prefer A to B and B to C, they must logically prefer A to C. This diagram shows event A, event B, and event C. Right now, we only know their order, not the distance between them. To measure that distance, the authors introduced probabilistic combinations to test the individual's preferences. They proposed a hypothetical choice, a guaranteed event A, or a 50-50 probability lottery of event B or C. If the individual prefers the guaranteed event A, they reveal crucial mathematical information. Their desire for A over B is strictly greater than B over C. By injecting an objective probability variable into a subjective choice, von Neumann extracted a precise numerical distance. We can push this further by fine-tuning the probability variable, alpha, until the individual is perfectly indifferent between the certainty and the lottery. We lock in a specific numerical ratio. This chart shows the mapping function, converting conceptual gaps directly onto a rigorous number line. Subjective choices now behave exactly like mathematical expectations. This numerical utility is defined up to a linear transformation. The 0 point shifts, but proportional distances remain perfectly rigid. Utility has now evolved from a vague psychological ranking into a robust numerical system capable of handling complex algebra. Von Neumann and Morgenstern proved that by combining subjective preference with objective probability, utility becomes fully operational. With numerical utility established, the behavior of participants in a social economy finally has a valid mathematical model. This diagram shows those precise numerical values slotted directly into the cells of a classic game theory payoff matrix. We are no longer trying to force the Robinson-Crusoe optimization model onto society. Behavior is now modeled as a rigorous game of strategy. This payoff matrix allows multiple interacting agents to calculate optimal strategies, even when they do not control all the variables in the system. This mathematical bedrock rapidly expanded from pure economic theory to applied real-world operations in the late 1940s and 50s. Institutions like the Rand Corporation adopted this framework to analyze military strategy, nuclear deterrence, and complex operations research. By quantifying human preference, the theory of games established the fundamental grammar for modeling rational human conflict and cooperation across every field from sociology to nuclear strategy.